let's take some time to look more closely at the enzymes that catalyze DNA synthesis, their functions, substrates, and requirements. As we've seen, DNA polymerase enzymes incorporate deoxyribonucleotides into a new strand of DNA using the original parent strands as templates. However, there exists more than one type of DNA polymerase. There are at least 5 in E. coli, with their respective jobs to perform. In comparing these enzymes, we want to consider their turnover number, the speed of the catalytic reaction. Also, we want to examine their processivity, that is, the number of nucleotides incorporated before the enzyme dissociates from the template DNA. The table below lists several items for comparison of DNA polymerase I, or POL1, with POL2 and POL3 enzymes. As you can see, they vary considerably in terms of size, number of subunits, and the extent of their functions. In addition, they vary with regard to turnover number and processivity. DNA polymerase III is the main replication enzyme, and it is perhaps not surprising that it has the highest turnover number and the greatest degree of processivity. Notice the 2 rows at the bottom of the table, showing that some polymerase enzymes also possess exonuclease functions. We've already considered that DNA polymerase must have a template to read, so that nucleotides may be incorporated based on complementary base pairing with the template. It must therefore have all 4 deoxyribonucleotide triphosphates as substrates. Due to the nature of the catalytic mechanism and the abundance of negative charges in this system, divalent magnesium is also required for catalysis. However, there is another limitation, and that is that DNA polymerase is unable to initiate de novo synthesis. Instead, it must build on an existing 3' OH end. This is accomplished in vivo by the synthesis of a short RNA primer that anneals to the end of the parent template. For this reason, all 4 ribonucleotide triphosphates are also required in order to generate the primer. Just as DNA polymerase III is the main replication enzyme, so other polymerase enzymes have distinct functions. POL1 is involved in repair and patching of DNA. POL2, POL4, and POL5 are all repair enzymes. In the table we examined in an earlier slide, we saw that some polymerase enzymes possess exonuclease activity. This is an important part of maintaining the fidelity of the replication process. This allows DNA polymerase III to remove incorrectly incorporated nucleotides as part of the proofreading process that occurs during replication. Some of these DNA polymerase enzymes function as exonucleases in repair mechanisms, removing and replacing incorporation errors after the replication process is complete. As you can see, the nature of the DNA genome and the essential nature of its correct replication necessitates highly specialized enzymes in order to complete the process.